Thank you for the kind introduction. Good morning everyone. I am Shobhan Maiti and today I will be talking about our work on a 415 nanowatt secure human body communication node for authentication and biophysical monitoring applications. This is a brief overview of my presentation today. I will start with the motivation behind this work. Then I will provide some background information about human body communication and its suitability for applications like this. Subsequently, I will go into the details of Electro-Quasistatic human body communication transceiver that we have designed, and finally I will discuss about the measured performance metrics and conclude. First, let's look into the motivation of this work. Over the last few decades, the size and cost of unit computing has reduced drastically following Moore's law. As a result, there is an abundance of small form factor wearable devices around us, which has given rise to applications like physiological health monitoring and secure authentication. Many of these applications require the transfer of a small amount of data among devices. Low data rate communication up to a few kbps is sufficient in these cases. However, these applications require low power and secure operation, and the communication method used by these devices play a key role in satisfying these requirements. Now let's look what do we mean by secure and low power communication. Here we have a scenario where two devices are communicating with each other through wireless communication using electromagnetic waves over the air. The transmitter transmits the electromagnetic signal in all directions in an isotropic manner, which is available to any device within a range of 5 meters. Hence, a malicious attacker can snoop the transmitted signal if it comes within the range of the transmitter and can potentially decipher the ongoing transmission. Now let's think of an alternate scenario, where the devices use the proximity of the human body to use it as the communication medium between themselves. This is known as human body communication, which I will commonly refer with the acronym HBC throughout the rest of this presentation. If done in the electroquasistatic regime, HBC can confine the signal within a few centimeters of the human body. As we can see from the blue aura around the body of the person on the right side. The ongoing transmission between the devices on the body is contained within 1 centimeter from the body and within 15 centimeter close to the transmitting device. In this scenario, an attacker has to come really close to the person and touch him to snoop the ongoing signal transmission, and will not be able to snoop the signal transmission at a distance as seen on the figure on the right side. Hence, electroquasistatic HBC reduces the private space of communication to a few centimeters compared to almost 5 meters for radio wave communication like Bluetooth. This shows how HBC can provide a secure communication medium as compared to wireless radio wave communication. Now let's look how HBC can also enable a low power communication channel and satisfy the other key requirement of these applications. State-of-the-art Bluetooth transceivers consumes power in the range of a few milliwatts. Previous low power implementation of HBC has achieved power consumption in the range of 40 microwatts as was presented in CICC 2016 and 2019. In this work, for the first time, we demonstrate sub-microwatt electroquasistatic HBC operation, providing an ideal low power communication method for secure authentication and physiological monitoring applications. Now let's look briefly into the background of human body communication. HBC was first proposed by Zimmerman in 1994. He proposed exciting a signal in a single-ended manner to the body through an electrode and also receiving it in a single-ended manner at the receiver end, which was commonly known as capacitive human body communication. In 2007, Cho et al. Proposed the first channel characterization of the human body. The same year, Song et al. Designed the first human body communication IC. Later, in 2010, Weidmuller proposed galvanic HBC, which uses a differential excitation at the transmitter and receiver end for signal transmission. Park et al. Proposed magnetic human body communication, where a coil is used at the transmitter to induce magnetic fields into the body and is received using a similar coil at the receiver. Recently, our group proposed electro-quasistatic human body communication, which operates in the electroquasistatic frequency range to confine signal within the body. Now let's look into the details of EQS HBC. We are all aware of Maxwell's law, which provides a relation between electric and magnetic fields for EM wave propagation. For EM waves, the electric and magnetic fields are interrelated to each other through their time derivatives, as we can see from the equations at the bottom. When one of these time derivatives is not important for calculating the overall fields, then the system becomes quasi-static. In electro-quasistatic scenario, the time derivative of the magnetic field can be ignored while calculating the overall electric field. This essentially puts a limit in the frequency of operation. Now let's see what this physically means in case of EQS HBC. If we look at the radio spectrum, it extends from 3 kHz to 300 GHz. The EQS regime falls in the kHz to a few MHz frequency range. But how do we determine the frequency range for electroquasistatic human body communication? The answer to this lies in the relation between the wavelength at the frequency of operation and the size of the human body. To operate in the EQS regime, the wavelength for operation has to be significantly larger than the size of the human body. Mathematically, it means the approximation error due to the electroquasistatic approximation needs to be less than 5% of the overall field. For example, if we do the maths for a frequency of 1 MHz, the approximation error comes out to be 1.4%, and it falls in the EQS regime. What all of this now means is that we can use a lumped circuit element model to model the human body communication channel. Now let's look how does the circuit model for EQS HBC look like. The HBC circuit model primarily consists of two kinds of capacitances. One is the return path capacitance of the transmitter and receiver device with the surrounding ground plane. The other is the parasitic capacitance of the body with the surrounding environment. Now all of this can be put together into a circuit model as shown here. Here we see with the capacitive termination at the receiver end, the overall channel loss is actually dependent on the capacitive ratio of the load and the parasitic capacitances. Now that we have an understanding of the background about HBC, let's see how we can use our understanding to design a low power and secure HBC transceiver. The channel response of the human body plays an important role in determining the overall design requirements of the HBC transceiver. As we can see from the simplified circuit model on the left, the overall channel characteristic is dependent on the terminating impedance of the channel. That is, the input impedance of the receiver. If we have a low impedance resistive termination like a 50 ohm termination at the receiver end, then the overall channel loss will exhibit a high pass response with high loss at low frequencies. Now, if we use a capacitive termination at the receiver, then the overall channel loss will be dependent on the ratio of capacitances, which will make it frequency independent. Eventually, there will be a roll-off at low frequencies due to the resistive component at the receiver end. However, the low frequency loss will be significantly reduced due to capacitive termination, as can be seen from the figure on the right hand side. This shows that our receiver needs to have a high input impedance, which is capacitive. Given the channel response, now let's see what kind of receiver architecture will be most optimal for the target applications. A broadband receiver is one of the design choices. But since our target data rate is low in the range of few kbps, that would mean operation in the low kilohertz frequency range. As we can see from the channel response, even with a high impedance capacitive termination, there is a roll-off at low frequencies. Hence, the channel loss will be high for broadband receiver requiring high sensitivity at the receiver, and hence a broadband architecture is not the most optimal. Upconverting the baseband data into frequencies with lower loss will relax the sensitivity requirement on the receiver and enable low power operation. However, it has a security implication. As the signal leakage out of the human body increases with frequency, it reduces the physical security of HBC. Hence, using a high enough carrier frequency which takes it out of the electro-quasistatic regime will hamper the physical security aspect. The optimum carrier frequency is in the range of 100 kHz to 1 MHz. In this frequency range, the channel loss is less and the signal is also confined within close proximity of the body. As the modulation technique, we use on-off keying for its simplicity. An OK transceiver with a sub-megahertz carrier is the optimum architecture satisfying the low power and security requirement. Now let's look into the different security aspects of this EQS HBC node. The physical security aspect is achieved by confining the signal within the body and denying the attacker from physically accessing the ongoing signal transmission. The frequency of operation plays a key role in determining the extent of physical security that can be achieved through EQS HBC. As can be seen from the measurement results on the left, the signal falls below the noise floor even for a distance as close as 5 cm away from the body when operating at a sub-megahertz frequency. The signal leakage is a little higher near the transmitting device but still falls below the noise floor at distances of 5 to 10 cm for a sub-megahertz operation. In contrast, we can see that for a frequency of 21 MHz, which is the standard operating frequency for the IEEE 802.15.6 HBC standard, the signal leakage is significantly higher and above the noise floor. As the frequency increases, the signal leakage also increases significantly. Hence, operating at the EQS regime provides us with the physical security. The mathematical security is achieved by encrypting the data using an AES-256 engine before transmitting it. The AES encryption happens over 14 rounds for 128-bit data blocks. The encryption enables standard security measures which is present also in today's wireless communication. To further enhance the physical security provided by EQS HBC, we use frequency hopping at the transmitter end. Although the signal is below the noise floor in the EQS regime, as we have seen in the previous slides, still one can use averaging and bandpass filtering to recover the transmitted data. Frequency hopping at the transmitter end will nullify the effect of any such averaging technique. This makes envelope detector based receiver suitable since the precise knowledge of carrier frequency will not be necessary at the receiver in this scenario. Now that we know of all the security measures and the architecture to be used for the receiver, let's look into the details of it. Here is the overall receiver architecture. The analog front end consists of an amplifier, followed by a passive envelope detector for down conversion. An integrator is used to clear up any carrier feed through into the envelope detector output. A regenerative latch-based sampler is used to convert the integrator output into digital bits. An integrating Muller-Muller baud rate CDR is used to maintain proper phase relation between the demodulated baseband data and the sampling clock. A multi-phase clock generator provides the CDR with 16 different clock phases. Now let's look into the details of some of these individual blocks. We use a double-stacked current-starved architecture for the front-end amplifier. The PSRR of the amplifier was a critical design choice. A two-stack current source amplifier provided better PSRR compared to a single-stack scenario, as we can see from this graph on the right side. Hence, we went with the two-stack architecture for our amplifier implementation. For the envelope detector, we have chosen a passive topology to reduce the overall power consumption. The tunable bias can be used to control the carrier feed through into the baseband output. The bias point can be tuned to choose the optimum operating point with the maximum ratio of baseband to carrier output. The given data rate is limited by the carrier feed through into the baseband data and plays a key role in minimizing the overall power consumption of the receiver. A resettable clocked integrator is used to reject the carrier feed through into the envelope detector output. The integrator gain is controlled to the value of the tail current source and the integration duration. With the same current source, a higher integration duration, hence a lower data rate, will provide higher gain, as we can see from the curves on the right hand side of the slide. Now let's look into the details of the transmitter design. The transmitter is fully synthesizable and generates the OK signal through direct digital synthesis. The baseband data can be loaded externally or generated internally from a PRBS generator. The data is encrypted before being coupled to the body for transmission. The frequency hopping is achieved by varying the division factor of the carrier clock and hence changing the carrier frequency of the OK transmission. Now that we have an understanding of the overall EQS HBC transceiver design, let's look into some of the measurement results obtained from this IC. This is a dye micrograph of the EQS HBC node. The proposed design is fabricated in TSMC 65 nanometer low power technology and has an area of 750 micron cross 450 micron. First, let's look into the transmitter power consumption. The graph on the left shows the transmitter power consumption across different frequencies for varying supply voltage. A low carrier frequency reduces the overall power consumption. The AES power consumption with varying data rate is shown on the right. As we can see, the data rate has negligible effect on the overall AES power consumption as it is dominated by the leakage power. Hence, having a low supply voltage at the transmitter end is necessary to reduce the overall power consumption. Here we look into the receiver performance. The first graph shows the bathtub curve for 10 kbps data rate, showing a 0.54 UI opening for a bit error rate of 10 to the power minus 5. The second graph shows the BER performance for varying frequency, keeping the data rate constant at 10 kbps. As the carrier frequency reduces, there is more and more feed through of the carrier into the baseband output. Hence, the bit error rate increases. The plot also shows that a carrier to baseband frequency ratio of 50 is necessary to maintain a bit error rate of 10 to the power minus 4. The third graph shows the input power versus bit error rate plot. For a minimum power mode, the sensitivity of the receiver is minus 64 dBm for a bit error rate of 10 to the power minus 3. The sensitivity can be increased to minus 72 dBm by operating at the higher power point. Now let's look into the power breakdown of different blocks within the EQS HBC node. The bar graphs on the left shows the breakdown of power consumption for different security measures. Physical security measures, that is the EQS HBC receiver, consumes most of the power as the supply voltage increases. Showing low voltage operation at the receiver is key for overall low power operation of the transceiver. The pie chart on the right shows the power breakdown at the minimum power operating mode, with a significant portion of the overall 415 nanowatt power being consumed by the leakage of AES and the RX standby power. The overall active power consumption in this scenario is 108 nanowatt with an operating supply voltage of 0.5 volts. Now let's look how these power numbers compare with other state-of-the-art HBC transceivers. Our work shows an 100x improvement in the power consumption compared to state-of-the-art HBC transceiver implementations. And also this achieves sub-microwatt HBC operation for the first time. It also simultaneously provides mathematical and physical security which is not present in any other HBC implementation previously made. Here we see a demonstration of a secure key exchange between a wearable device and a computer using the EQS HBC node. When the person touches the receiver connected to the computer, a secure key is transferred from the wearable device through the person's body to the computer. This is the PCB that is being used for this particular demonstration. Here are the waveforms for the secure key transfer. We can see the baseband data being OK modulated and transferred through the body, which is then demodulated with a clock cycle delay at the receiver end. The last waveform shows the captured leakage 1 cm away from the person transferring the key from the wearable to the computer. And we can see there is no perceivable signal leakage out of the body. This further demonstrates the physical security aspect of electro-quasistatic human body communication. Now I will conclude the presentation. So to summarize, in this paper we have proposed a physically and mathematically secure sub-microwatt electro-quasistatic human body communication node for low data rate but security sensitive applications like secure authentication and physiological signal monitoring. At the low power mode at 1 kbps data rate, the transceiver consumes 415 nanowatt power, which is a 100x improvement over state-of-the-art HBC transceivers. This can potentially open up new directions towards battery-less wearable nodes in the future. I would like to thank you for your attention and I will be happy to answer your questions.